Okay, welcome to the next class on multiple view geometry. Over the last classes we talked about how to model the camera motion, how to model the perspective projection onto the image, and now we will get closer to actually the images and how to acquire information from images. What we've seen so far is that we saw how images are formed, how points are projected into images, and then the goal is, once we have the points in the images or lines in the image, to invert the process and reconstruct the geometry. Unfortunately, as you know, once we see images, we don't actually see points, but we see colors. And so one of the challenges that I will talk about today is how to get from points, from colors in the image to points. So how to get from photometry, meaning intensities, brightness values, to a concept of points. And then the idea is, once you have points, you can try to put them in correspondence and infer their 3D location. And so there is geometric information, but in some sense that geometric information is hidden in a multitude of colored pixels. We don't actually observe points in the real world, but we rather observe colors. And as you recall, the multiple view reconstruction started in the early days with Krupa's results even in 1913 already. But what he was considering was the problem of observing points in the world. And now if you hold a camera into the world, you don't have points, you have colors. And so typically there's one way to go about this, and that is the standard computer vision pipeline to do 3D reconstruction, the one that has been most successful until these days. And that is that you identify points in the image that are associated with some characteristic image structure, that are in some sense unique compared to the rest of the image, so that you're actually able to identify the same point if you see it in a new image. Typically something like a corner or something that is characteristic. You're going to have a hard time, identifying this point as a characteristic point, but possibly the corner of the board may be sufficiently unique so that if you get a new image of that board, you can say there's the same corner. And you want to associate points that correspond, and so you have to find points that are in some sense sufficiently unique or characterized uniquely. And this is a challenge, and so there's been a lot of work in computer vision over the last 30 years and very intensely over the last 10 years even, to develop very sophisticated feature descriptors that ideally uniquely characterize each point, so that you can distinguish that point from a different point. And the challenge there is there are multiple. First, the characterization should be unique. That feature vector that you associate with the pixel should tell you which pixel you're looking at. But at the same time, it should be invariant, meaning if I zoom out or if I move the camera around, the same pixel should ideally have the same feature vector at any given time. And so this is quite a challenge to devise feature descriptors that have these properties that are invariant to rigid body motion of the camera and to certain transformations, to illumination changes. If someone comes in and switches on the light, you want to still be able to find the same point even after the light was switched on. Although things have changed, so you want descriptors that are robust or invariant to these transformations. And so this is quite a challenge, and I will briefly describe some of the key concepts here. Once you have identified points, then you can put them in correspondence and you can try to infer geometry in this way. One should be aware that this approach to solve the problem is suboptimal. We are given an image with lots of information in it, very rich, detailed information, colors everywhere, and then we just select a few hundred points and say, these are the points I look at. And then we hope to recover the world, the geometry of the world, from just a few hundred points that we selected from the image in some fashion. The hope is that in some sense this point is more informative than any point on the white blackboard, and you're going to agree this is quite likely the case. Nevertheless, the information on the blackboard, the small brightness variations here, they also contain information about where the camera is, about where points are in the world. And what we do by selecting a few feature points and working with these only is we just drop a lot of potentially useful information. That should be kept in mind. We throw away a large amount of information by selecting a small set of feature points. Yet, I wrote this here, retaining all image information, all colors and brightness values of every image is computationally challenging. I had slides a few years ago where it said computationally infeasible. This is not true any longer. You can use all the information, and these are so-called dense methods, dense tracking, dense reconstruction algorithms. You can do it nowadays partially by relying on graphics hardware to compute things efficiently. But nevertheless, in this class I will focus on the somewhat more classical pipeline. I may say a few words towards the end about dense reconstruction algorithms and about how they work, but these emerged only in the last 2 or 3 years. And the classical pipeline, the one that has been shown to actually work in real time, where you can track a camera in real time and reconstruct geometry in real time while the camera is moving, this pipeline was shown to work in real time on this more traditional feature point based techniques. And this has actually been shown to work in real time camera tracking, real-time reconstruction of feature point locations in 3D. The first real-time approaches emerged around 2000, so already 13 years ago. The first dense real-time approaches emerged 2 or 3 years ago. So there is, you know, a substantial more additional amount of computation that you have to do to really make use of all colors. And nowadays, we're looking into a domain where computation time becomes important again. Often people say, oh, the computers got faster, now we can do more things. Yeah, but while the computers and the personal computer got more and more powerful, having big graphics cards, etc., to do huge computations, a large area of applications, as you know, is the smartphone domain, where we don't have a very powerful PC, we don't have a graphics card on the smartphone, at least not any graphics card that can do big computations. And still there's a huge demand for algorithms to run on these lightweight small devices. And so for this reason, that the more traditional sparse approach that uses only few feature points will still be important for many years to come, because it's more, you know, it's more slim in terms of how much computation you have to do. This is an example of how these feature point approaches work to give you an idea of where we're heading. We have a set of images here, for example, 2 images from a sequence. We extract a subset of feature points. These are the red points marked here. You can see them, small red points. And then we can find the same feature points in the subsequent images. The camera is moving. We have a small displacement from one image to the next. The object moves, or the camera moves in our case. And then you can track these points from one frame to the next. And once you track them from one frame to the next, you have a correspondence across the frames. You can say this point here at the top of the J, of the letter J, is here in the next image. And this way you get a set of correspondences over time. You can track where does this point go over time. And with these correspondences, we have point correspondences, and we can try to infer the camera location and the 3D location of point. And this is what you see here. These are reconstructions that were generated, a wireframe reconstruction, then a reconstruction with a texture map superimposed, that were computed using this sequence. Here's actually the sequence. So on the left you see a set of images and how they are tracked. You see the motion is very small actually. So there is not a lot of motion. In fact, these techniques work very well in the so-called small displacement case, in the case where you have little motion from one frame to the next. The way nowadays we can assure, even in more challenging scenarios, that we have small displacements is by taking cameras that have higher frame rates. So interestingly, computer vision becomes easier with higher frame rate. If you have not 30 images a second, but 60 images a second, then typically the displacement from one frame to the next is only half as large if you have the same camera motion. And so you are more and more in the regime of small displacements, and this is where these techniques work well. They track the points, and then from these point correspondences, they can compute the camera locations, they can compute how the camera moved, and they can compute a wireframe model. How accurate the reconstruction is sometimes hard to say if you just see, in particular, if you see the textured model. So what you see here towards the end is the reconstruction with the texture superimposed. This can be very misleading. If someone shows you his best reconstruction algorithm and shows it to you with the texture superimposed, you should be careful. If you want to reconstruct a face, for example, it suffices that you take an egg and project the texture on it. Looks quite good, actually. Although the geometry is very suboptimal, you know, if you just see the geometry, you're going to say, it's not a face, it's an egg. But once you project the texture on top, it can be misleading. You see details that are not in the geometry, that are just in the projected color. In particular, if you go as far as doing what's called view-dependent texture mapping. So what you want in reconstruction is often you want to see what is a new view of the scene. What would this scene look like if I looked at it from that vantage point? View-dependent texture mapping means you take the geometry and then you say, before you render it, you say, where is the new view going to be generated from? Where is the virtual camera standing? And then you select for the texture map those images that are closest to that viewpoint and use these in the texture mapping in a way that the geometric details that are apparent in the texture are most consistent still, because you have almost the same viewpoint, to the extent that sometimes reconstructions are in a way that you almost feel that someone is just, you know, re-projecting you the same images that were acquired in the first place. So that's, I just wanted to say that up front. Check textures reconstructions just visually, you know, comparing to the model is not a good way to quantitatively evaluate the performance.
Do we have a better reconstruction with small displacements or larger displacements?
There is a trade-off, interestingly. So the question is small displacement better for reconstruction or large displacement? Small displacement is better for tracking points over time. I'll show you later on the wide baseline case, the large displacement case, and there it's actually difficult to find correspondences. So that's going to be easier in the small displacement case. On the other hand, you can imagine from a geometric point of view, the triangulation that I do to get 3D location is more reliable if there is a wider baseline. And so what you often do in practice is you try to combine the advantages of both methods, meaning you track these points over multiple frames, and then you use the most extreme frames to do the triangulation. So the tracking is done in the small baseline case, but over time the baseline grows, and then you can hope to get more reliable reconstructions with the larger baseline. So there is a certain trade-off there. And you can imagine one of the difficulties is if you make errors in the tracking, and what I just said, tracking over multiple frames, you have a risk of accumulating these errors. You make a little bit of an error in every single frame, but from frame 1 to frame 20, there may be a large accumulated error. This is called drift. And if you have that drift, and if you have inaccurate correspondences, that can quite well generate very inaccurate reconstructions. So one of the challenges that we'll talk about in the class is how to make reconstructions robust. Robust in the sense that if the correspondences are not perfect, but slightly off, that the reconstruction is ideally also only slightly off. That is not always the case, unfortunately, so we don't always have this notion of stability, and one of the challenges, and that is still to some extent an open challenge, is how to make things robust. That they work with real-world conditions where tracking can sometimes fail. So this is the idea of tracking. Here is an example of the more wide baseline case, of the large displacement case. The same object seen from different viewpoints. And this is a nasty case, not just because I have a substantial change in viewpoint, in translation and rotation of the camera, but also because the object is what's called non-Lambertian. It's an object that is shiny, that is slightly reflecting, see the nose for example, and the consequence is that the same structure, once I look at it from different viewpoints, has a very different brightness, a different appearance. Here, for example, the lower lip of the statue is very shiny. The same point seen from a different view, from a different camera, is not shiny at all. So if you compare the colors and brightnesses in these two patches, chances are they're not going to be very similar. And so the question is, how can a machine identify that this point corresponds to that point? It's a very difficult problem. Similarly here, you know, this is essentially Lambertian. This is black and white, so it's actually fairly simple. But you see the same point in the two images is different because it's rotated. Here, the black corner is in the top left. Here, the black corner is on the side because we've had motion from one to the next. So taking into account the fact that things get distorted with larger viewpoint changes makes the whole correspondence finding very challenging. And ultimately, the difficulty in the large baseline case is that matching and correspondence becomes a combinatorial problem. If I say small baseline, the camera moves little bit, little translation, little rotation, that implies that also points in the world will have shifted only a little bit from one image to the next. And that means I can say, I don't know where my corresponding partner is for any point here, but it must be in some vicinity. I can search the neighborhood. If someone says, well, I don't actually know that it was a small baseline case, could have been a large camera motion, that essentially means your corresponding partner could be almost anywhere in the image. And that, of course, is nasty because you have a lot of pixels in the image, and if any of them could be your corresponding partner, then you're going to search for a long time. And then you're going to have multiple partners that look alike. So, you know, in a checkerboard pattern, there's going to be tons of points that have the same appearance all over. And so this is a nasty case for in the wide baseline case, if I have repetitive structures in the image, even if they're highly informative, you know, in the sense that the structure is somewhat characteristic, I have the same structure in multiple locations. I have a lot of ambiguities, and these are very hard to you know, prune out. So it's a difficult problem. In fact, this correspondence problem that you see here in these images is probably the most challenging problem in computer vision. It is a problem that reappears almost everywhere in computer vision. In 3D reconstruction from multiple views, we have to associate corresponding points in the image. This is a correspondence problem. If you track a person in a video and the person moves, you want to find corresponding points as well. So very often you have this aspect of correspondence finding. If you want to compare 3D objects and match them, you have to find correspondences between the points. So finding correspondences is one of the major algorithmic challenges. In addition, typically we will assume in what we do that we have rigid transformations, because in this class we will assume that the world is static and that the only thing that moves is the camera. And the camera, as we know, does a rigid transformation, rotation, translation. So any movement we see from one image to the next is going to be a 3D rigid body motion. Nothing but that. In real-world cases, we have what's called non-rigid motion or non-rigid deformations. That is deformations where, say, you have two faces from one image to the next and they change, The person rotates the head, so it's not the whole person rotating, but just the head, so there is an articulation there. In addition, all of a sudden, this is my co-author, Christoph Gütter, he starts to smile, so the whole face looks different, so there is deformations here. And then there's things like occlusions, that the same structure in one image looks completely different in another image, so we need algorithms that can identify correspondence even over substantial deformations where the head rotates substantially, and despite occlusions, despite changes in the appearance. For example, if you're going to say, where is the point that corresponds to one part of the teeth here, where is it in the other image? It's not there. There is no corresponding point. So you see that in many cases, the correspondence problem is even more nasty, because quite possibly a given point doesn't have a partner in the other image. And then, you want to make sure that this aspect doesn't screw up the correspondence finding for the remaining points, which do have a partner. Here's, for example, the result of this algorithm. This is a video. So here you see we have nowadays algorithms that can find correspondence despite substantial deformations. They can basically warp one image into the other, and this is what you see in this video here. So given the two images, the algorithm can warp, and then you can superimpose the lines of one image over the other, and you see with the sunglasses that it's a fairly good match, so that the correspondence is found fairly well. So these algorithms exist, and in fact nowadays this is a dense correspondence algorithm that actually uses all colors and images, and these algorithms nowadays work in real time. You can get them to work at up to, say, 60 frames per second on standard resolution. So as I mentioned, there is these two cases that you typically distinguish. Why do we distinguish them? Because there is different algorithms and different methods that we use. In the small deformation case, this is often the case which is referred to as optical flow estimation problem, where you say, I assume that the displacement is small, that my corresponding partner is in the vicinity, and there are algorithms to find correspondence either sparsely, this is the so-called Lucas-Canade method, or densely, and this was started by Horn and Schank. Interestingly, both of these methods are similar, and both were published at the same time in 1981. So for correspondence finding, for optical flow estimation and these types of problems, 1981 was one of the breakthrough times in the field of computer vision. So these are quite important papers, and in this class I will focus on the Lucas-Canade method, because in this class we will not spend much time on so-called dense methods. I'm teaching another class in fall on variational methods, and this is where we go into the dense methods. But here, for the sake of simplicity, I will stick with the more simple Lucas-Canade approach that I will briefly review in this class. What they find is they find a small displacement for certain pixels, ideally every pixel, but at least a certain subset of pixels, where they say this is where that pixel moved, or where the object moved, or where the corresponding partner is in the new image. The wide baseline case is, as I said, a different case. And in that case, we don't have the small motion assumption anymore. We may have substantial motion. And this is different in the sense that in the wide baseline case, to date, people use different algorithms. They don't just use the local brightness to check where the partner is, because points of similar brightness, if I allow partners to be everywhere in the image, I will have tons of points that have similar brightness. If you say, where is this point in the other image, you know, there's a lot of white points in the room. If you constrain yourself to the neighborhood, that may work, but in a larger environment, in the wide baseline scenario, this is not going to work. And then you have to devise what I mentioned, these more sophisticated feature descriptors, and you have to pair feature points. And then you don't use the neighborhood information as much anymore, but you use the feature descriptor. And you have a very detailed, long, say, 100 component vector to describe every point. And then you say, where is, in the list of other points in the other image, where is a point that has a similar feature descriptor? And then you say, okay, these may be partners because the descriptor vectors are similar. And then you keep your fingers crossed that they really are partners, because if not, that really messes things up. Or what you do is then you add an algorithm on top of it that kind of prunes out the wrong correspondences, that uses a lot of paired correspondences, computes a reconstruction, and checks which ones of these points don't match, are not consistent with that reconstruction. And then you say, okay, maybe these were not the right partners, so you kick those out and you iterate. And then you hope that the thing converges to the right solution. It's a somewhat involved business, you can imagine. So this is the wide baseline case, and it involves feature points and feature descriptors for matching. In this class, I will focus more on the small deformation case, and in fact, what we see over the last years is that the boundary between the small deformation and the wide baseline is a moving boundary, in the sense that with advances in the optical flow estimation field, we can push the limits of what is still a small deformation. For example, once you do coarse-to-fine algorithms, and a lot of the optical flow methods are implemented in a coarse-to-fine manner, then a large displacement on a coarser scale of the image is a small displacement. And so you can try to estimate correspondences on a very coarse scale, where you just coarsen the image in say, a pyramid. You start with a fine resolution, you go to a very coarse resolution, and on the coarse scale, you compute small displacements that you then propagate to the finer scales. And that way you can get small deformations in optical flow estimation methods, but all the way to about 20 pixel displacements, which are not that small after all. And so the limit of where the wide baseline algorithms start and where you can go with small deformations is changing. And this is why I decided to focus on the small deformation case. It's somewhat more transparent than the wide baseline pipeline. The other thing is that nowadays a lot of the domains where reconstruction becomes interesting is the real-time domains, where you have a moving camera. And if you have a moving camera that someone moves, then typically you are in the small baseline case, in the small deformation case, because especially with a faster camera, because you move incrementally. So this is a different regime than, say, taking a digital camera, doing a snapshot, then walking around, taking, say, only 10 or 20 snapshots. That's not the small baseline case, but nowadays a lot of people are interested in, can you do with a handheld video camera, can you reconstruct? And fortunately there we are in the small deformation case, most of the time. And what we see is we have algorithms that can do reconstructions even in real time from a handheld camera, unless you jerk the camera. If you jerk the camera, then you lose the small baseline assumption, and then the methods often fail. Here's the small deformation case. As I said, we assume the scene is static, the camera is moving, and so any point in the plane is going to move according to a rigid body transformation. Here we have the rigid body transformation, and then we can show that the coordinate corresponding to a point x1 in the second image, you remember there's the scale factor lambda in the perspective from the perspective projection, and so the transformation from x1 to x2 can be written as a function h of x. That's what I call the function that maps from x1 to the new coordinate x2. And this is a rigid body motion. Lambda 1 x1 is actually the, remember that is the 3D coordinate, right? If I have a point x, large x in the world, and I consider the coordinates of the first camera as my reference frame, then this is the same as lambda 1 times small x1. Right, so here's the point x in the world, here is my camera center, here's the image plane. The image plane has a distance 1 from the camera, so this is little x1 in homogeneous coordinates, and if I scale with lambda 1, this is lambda 1, then I get the point large x. And so this is the point large x, represented as a function of the 2D coordinates of the point in the first image, and then I rotate and translate that into the new coordinate frame, and if I divide by the lengths with respect to the second image, so now I have another image here. This is the scenario. We look at the same point in another image, and this is what we call lambda 2, is the lengths, the distance from the camera center of the second camera. And so that is then the point x2. So this image basically characterizes what a lot of the things we will study in the class, so it's a very important image. We're looking at some structure in the world. We have a camera that moves around. It rotates and translates. And then we look at the same structure from a new vantage point, and then the coordinate in the first image is transformed to some coordinate in the second image. And that transformation is what I wrote here. So it is x1 lambda 1 is this point, large x. Large x is lambda 1 small x1. Then I transform it into the coordinates of the new camera, of the second camera, by rotation and translation. So I get that point, but with respect to these coordinates, and if I divide by lambda 2, then I get this point x2. And so this is the mapping from the first image to the second image is the function h, and in general it's a somewhat nasty transformation because I divide by lambda 2, etc. But you can approximate it in many ways. In the small baseline case, we assume rotation is small, translation is small, and so if we neglect the rotation and just focus on translation, we can approximate it by just a shift. So we say if we have a little motion of the camera, then points just translate in a first approximation. We can approximate this somewhat more accurately by saying we allow an affine transformation. That is, we have a function h that is ax times b, where a is a matrix. Why do we do these approximations? Because they're linear. They're linear transformations. The simplest linear transformation is just an offset, or not linear, but affine. And you remember in homogeneous coordinates, we can write them as linear transformation. In fact, here's the formulation of this affine transformation. We can write it as an offset, a displacement. So the new coordinate is the old coordinate plus some offset we call u of x, that is a displacement. So this is just a rewriting. Rather than having a function that maps from the old coordinate x1 to the new coordinate x2, we can also say it should be x plus some offset u of x. So at any point we have a vector that tells me where this point. So imagine we're looking at the image plane now. Here's the point x1. The camera moves, sees the same point again, and in the new image it's somewhere else. Here's x2 if I draw them into the same image plane, and this offset vector we call u of x1. This is a vector at each point that tells me where does this point move. And in the case of affine transformations, if I assume I have an affine transformation, then u can be written in this way. This looks a little complicated at the first glance. It's a matrix, a 6 by 2 matrix, xy1, xy1, the rest is 0. And then I multiply with some parameter vector that has 6 components, p1 through p6. Imagine you do that multiplication. What you get in the first coordinate, you get a 2-coordinate vector. The first coordinate, you get x times p1 plus y times p2 plus p3. Right? If I write that down, then I get u of x is p1x plus p2y plus p3. And the second component is p4x plus p5y plus p6. So I have a vector that has 2 components and they are linear or affine in x and y. Why is it useful to have these linear representations of u? It is useful. Oh, and then the third component is 1. It is useful because you can write it as a linear transformation. Right? It's a matrix that is space dependent and a parameter vector, but if I say everything in the image in that, say, neighborhood at least, moves in an affine transformation, then the vector p is actually the same for all points. It's just one vector p, 6 components that describe motion in an entire neighborhood, if you will. So you see we have different kinds of motion models that we can use to approximate the real rigid body motion.
What is our parameter vector? Is it rotation translation?
Yes, and more actually. If the matrix A that you have here is a rotation matrix, in this case a planar rotation, remember this these are the 2D coordinates, so there is an angle by which we rotate. If this is a rotation matrix, then it would be rotation translation. A can in general be more than rotation, so there can be a sharing as well, if you will. But it's some matrix with 4 components, so there are 6 parameters. Rotation and translation would only be 3 parameters. Translation and then 1 angle to rotate. Here we have 6 parameters, so we can model more than rotation, we can model affine motions. What this includes is shrinking motion and divergent motion. So for example, motion where everything moves towards some common center, this is an affine motion. But then rotation is also an affine motion, or the inverse, the divergent motion where we move outwards, these are all affine motions. But the reason why we use affine is to have a general matrix and 6 free parameters. As you remember, rotations are a bit nasty to represent. We just had that. You'd have to go to Lie algebra, so you have the matrix that contains sine and cosine of some angle, and then you optimize in the angle, and you just don't want to do that complication, so you say we allow a little more in terms of motion fields, a little more freedom. It includes rotations, but it's more, and we have an easy access to the parameters. This is why often when people model rigid body motion, they use an affine model to represent the rigid body motion. It just simplifies the computation, and it often allows more general motion. For example, if I move an object towards the camera, then what I expect is this kind of divergent motion. Things will move outward or inward with respect to some center of focus of expansion. And that is not a rotational motion, and it's not a translational motion. It is translational in 3D, but we're talking about 2D motion here. Small x are the 2D coordinates, so the perceived motion in the image plane is a divergent motion. It's not a translation. And the nice thing is this is all included in these affine transformations. So what we have here is we just use various parametric models of motion. Why we do that, we'll see that in a second. And this is used in the optical flow estimation scenario. So optical flow is the aim of optical flow is to estimate motion fields, and often in the literature you see the terms optical flow field and motion field used exchangeably. Strictly speaking, there is a difference. Strictly speaking, the optical flow field is a motion field, but only on the image plane. So it's sometimes called the apparent motion. So it is whatever motion you see in the image plane. So if I have a point that moves exactly toward the camera, although this point is moving, you don't see a motion in the camera. And so the apparent motion is 0, but its real motion is of course non-zero. And so the optical flow refers to that aspect of the motion field that can be seen in the image. So it's in some sense the projection of the real motion onto the image plane. That is the so-called optical flow. And the challenge is, and there's been much research, thousands of papers over the last 3 or 4 decades on estimating optical flow. On how to compute, given 2 or more images from a video, how to compute where things moved from one frame to the next. This is the challenge in optical flow. And yes. And so this is the distinction between the optical flow and the real motion in 3D. So when someone says, I do motion estimation, estimating motion from videos, you have to check, is it the apparent motion in the image plane, or is someone actually computing motion in 3D? And the estimation of motion in 3D is difficult because you don't see the third component. This optical flow estimation problem, so that is the problem of motion estimation that focuses on the aspects that you can actually see and observe in the image, 2D motion estimation. This was pioneered by 2 seminal works in 1981, as I mentioned, Lucas Canade, one of the methods, Horn and Schunk, the other method. And in fact, although these works are quite old already, they're now more than 30 years old, they are quite influential still to date. And some of these researchers are still active actually. So Takeo Kanade is at CMU. I think he's officially retired now, but you still see him jumping around on conferences here and there. Similarly, Horn, at the time at MIT, he's also still active and he's giving talks on conferences. Both of these methods I didn't check exactly, but they've been cited thousands of times. And so this is what you always hope for when you're in research, is that one day that you write a paper that receives thousands of citations. And these works were such influential works, and this is when people say these are works that had a substantial impact on science. Interestingly, they popped up in the same year, and this is actually not so uncommon in sciences. In retrospect, sometimes it's surprising to say, whoa, how could that happen? You know, for years people work on a problem and then essentially simultaneously people propose a solution. That is not so uncommon. And you see it over and over that people work on a problem, work very fervently, and then things pop up. And often in the literature you say, oh, these works were developed independently. that is true to some extent. You know, there's always a little bit of dependency just by the fact that they happen in the same year. There's often in research things are in the air. There's prior work and people see, and all of a sudden all that needs to be done is putting two pieces of a puzzle together. And if the two pieces of the puzzle were proposed a year earlier, then it's not surprising that multiple people see, hey, we can put this together and get a new method out. And so in a similar fashion, this appeared kind of in 1981. Interestingly, though, these two approaches are not identical. They are complementary in the sense that the Lucas-Kanade method is a sparse method, and it's somewhat simpler to read. You need a little bit less of mathematics to understand it. It's a method that says, I want to estimate the motion at any given point, and I assume that the whole neighborhood moves in the same fashion. So you assume that the motion is constant in a certain vicinity. The horn and chunk method is not a sparse method, but a dense method. It says, I want to estimate motion at every pixel, not just a few selected pixels, but really every pixel of the image. And then it doesn't assume that the motion is constant from one pixel to the next, but it assumes that the motion is smooth, so that the motion vector from one point to the next point changes only a little bit. So if you have the pixels of your image here, you have a flow vector there, and the flow vector next to it is maybe not identically the same, but similar. And this assumption is a fairly good assumption to represent the world. For example, if I move my arm here, then in the camera you see motion at every pixel of my hand, and indeed, you know, a pixel next to it is likely to have the same displacement vector, is likely to have a same or at least similar motion. And if I rotate, or if I move non-rigidly, it's not going to be exactly the same motion, but it's going to be similar. And so the horn and chunk approach is one of these dense methods, and in fact it is one of the first dense approaches in computer vision. When you look at the history and at citations of these methods, interestingly, the Lucas-Kanade method was more successful in the early years. Because it's simpler, because everyone can understand it, and because it is easy to implement and it is fairly fast. It is fairly real-time capable, and you can do tracking with the Lucas-Kanade method, and you could do it in real time decades ago. The horn and chunk method in the early times was not as influential, but has become more increasingly popular over the last years. And nowadays, so whereas say in the 90s, optical flow methods were mostly using the Lucas-Kanade concept of sparse flow vectors, modern optical flow algorithms tend to follow the horn and chunk approach. And that is because while the horn and chunk was not real-time capable in the 80s or 90s, now it is. Now we have GPUs, now we can actually solve these problems in real time. And so in the optical flow community, the horn and chunk approach has become maybe the prototypical approach for most modern competitive flow algorithms. Nevertheless, in this class, as I said, we'll focus on the Lucas-Kanade method. It's an elegant and simple method, and it can be implemented efficiently even on small hardware. Here's the assumption, and in fact horn and chunk is not so different from Lucas-Kanade on what assumptions are made. The key assumption in most optical flow algorithms is the assumption of brightness constancy. Brightness constancy may be a little misleading because today we typically work with color images, but then you say color constancy assumption. So it's essentially the same idea. A lot of these algorithms, they don't really care whether the image is a gray value image or a color image. A lot of algorithms you can straightforwardly extend to color. Not all algorithms, but in this case, whether you assume color is constant or brightness is constant doesn't really matter. In fact, a lot of algorithms that we see nowadays work just as well with brightness as with color. Often you see that for optical flow estimation, color doesn't seem to bring substantial advantages. The assumption is as follows. Let's say you have a point X that moves in space. Of course, in our class, we will focus, I said, on a static world and the camera is moving, but it doesn't really matter whether the camera, for this scenario of correspondence finding, it doesn't matter whether the camera moves or whether the world moves, you want to find correspondences. So let's assume static camera and moving points. This is exchangeable in this setting. So x of t is the coordinate of that point at time t. So this tells me where is the point x, where is the object point at what pixel coordinate at time t. And I of x and t is my video. So that is a brightness associated with every pixel x and every time t. So I have a family of images parameterized in t, and at each coordinate I can read out its brightness. And now the assumption is that the object point that I'm tracking keeps its brightness. From one image to the next it has the same brightness. That is the assumption. And so that is to say, if I read out the brightness at the location where that point is at the time t, for time t it's constant. So there is a twofold, this is important, it's a bit confusing, but important to separate. There is a twofold dependency on time here. The second dependency is that I have images at a later time, and the first one is that I evaluate this image at the location where that point is at the time t. So the location where I evaluate changes with time, and so that gives me this twofold time dependency. Maybe a few words about this assumption. The brightness constancy assumption is a fairly strong assumption. And as with most assumptions in image processing and computer vision, it doesn't hold. This is what we do when we solve image processing problems. We have to make a number of assumptions, and we make them even if we know they don't actually hold. For example, if the sun if there's a cloud in front of the sun and then the sun comes out, then things change in brightness. So even the same point will not be constant in time. Even worse, there's a lot of cameras where the camera does an automatic gain control. You've seen it in the old YouTube videos that the brightness changes. And so the brightness constancy is not actually fulfilled. Even if the world has constant brightness and you have a consumer camera, the brightness oscillates. The same points have different brightness. And so this assumption is not valid. Nevertheless, we make use of it, and the idea is that it holds approximately. But we saw also that if you have shiny objects and you change the viewpoint, then the colors can change as well. So there's many reasons why brightness is not exactly fulfilled. But I mean, if you look at it from another vantage point and say, if I don't make that assumption, then what can I do? If I assume any point from one moment to the next can arbitrarily change its color, well, then you can't compute correspondence. It's hopeless. If a point can, like a chameleon, take on a random color at any given moment, then there's no way you will ever compute correspondence. So you have to make some kind of assumption of this type. There are somewhat improved assumptions. For example, you can assume that the local gradient is constant, so that the change of brightness at that point doesn't change. Then you have some robustness to additive changes of brightness. But typically, these kinds of assumptions are made. I see we're running out of time, and we'll stop here, and I'll continue next time. Thank you.